Right, let's just dive straight into this chapter explainer. We're going to build the foundational toolbox you'll need to decode the physical universe. Think of this as your ultimate survival guide for mastering this specific physics chapter. Because look, physics isn't just about abstract, floaty concepts in a textbook, it is fundamentally about measuring reality. But before we can calculate the trajectory of a rocket or the density of a star, we all have to agree on how to describe what we're actually looking at.
Imagine trying to build a spaceship with a bunch of international partners, but everyone is using completely different rulers. You'd have one team over here measuring in feet and pounds, another using centimeters and grams, and maybe a third using meters and kilograms. It would be absolute unmitigated chaos. And honestly, until quite recently, that is exactly how science operated. We had all these scattered systems like CGS, FPS, and MKS making collaboration a total nightmare. We desperately needed a universal standard.
So, to solve that problem, here is our agenda for today. We'll be looking at the language of measurement, the international system, mastering significant figures, the dimensions of the universe, and finally, my absolute favorite, the physics cheat code.
All right, Section 1, the language of measurement. Let's start building that foundation.
Think of measurement kind of like an alphabet. We have a few independent base units. These are our fundamental letters. And literally everything else in the entire universe is just a combination of those base units. We call those combinations derived units. Together, the base units and derived units give us a complete cohesive system that lets us describe everything from the speed of a car down the highway to the pressure building inside a balloon.
Moving on to Section 2, the international system, or what we can call the 7 pillars of reality.
Remember that chaos I mentioned earlier? Well, the ultimate fix was the System International, or the SI system. Developed back in 1971, it sets out the 7 fundamental pillars that quantify all of physical reality. You've got the meter for length, the kilogram for mass, the second for time, the ampere for electric current, the Kelvin for temperature, the mole for the amount of a substance, and the candela for luminous intensity. If you want to measure anything, and I mean anything in the known universe, it all boils down to these 7 base quantities.
Oh, and besides those core 7, we also have 2 special dimensionless units specifically for measuring angles. We use the radian for flat 2-dimensional plane angles and the stereadian for 3-dimensional solid angles, like if you were measuring the spread of a beam of light coming out of a flashlight.
All right, Section 3, mastering significant figures. It is time to start dealing with actual reality.
Let's be real for a second. Pure math is absolutely perfect, but real-world measuring instruments, they definitely have limits. Every measurement you take involves some tiny bit of error, and we need a way to honestly report our data without bragging about precision we don't actually have. That brings us to significant figures. They aren't just tedious math rules you have to memorize for a test. They are the scientific way to show exactly how precise your tool was. If you time a pendulum swing at 1.62 seconds, that 1 and that 6 are absolutely certain. But that final 2? That's an estimate. It's your first uncertain digit. Writing down 1.62000 would be a flat-out lie because your stopwatch just isn't that good.
Now, what's really interesting about these rules is how simple they actually are once you realize they just exist to prevent us from claiming false precision. Non-zero numbers, they always count. Zeros sandwiched between them also count. But trailing zeros, those are the tricky ones. In a big number without a decimal, like 123,000 millimeters, those trailing zeros are just placeholders. They're not significant. But if there is a decimal, like 3.500, those zeros are proudly declaring, hey, I measured exactly to this tiny fraction. To avoid all this confusion, scientists absolutely love scientific notation because every single digit in the base number is guaranteed to be significant.
Let's actually see how this builds in practice. When you do math with these measurements, your final result can never, ever be more accurate than your original data. If you multiply or divide, your final answer is only allowed to have as many significant figures as your least precise measurement. Period. Take this example. Mass has 4 significant figures, but volume only has 3. So even though your calculator will eagerly spit out 1.688047 and so on, you have to rein it in. You must round your density to 3 significant figures, making it 1.69 grams per cubic centimeter. But, and this is a huge but, watch out, because when you switch to adding or subtracting, the rule changes completely. It becomes all about the number of decimal places, not the total significant figures. Say you add 436.32 grams to 227.2 grams. Your least precise measurement there only goes to 1 decimal place.
So your final answer has to be rounded off to 1 decimal place, giving you exactly 663.8 grams.
Okay, Section 4, Dimensions of the Universe, diving into the MLT framework.
Have you ever been right in the middle of solving a physics problem, maybe you're calculating energy or velocity, and suddenly you start panicking that your final equation is just total nonsense? What if you can't remember if a variable is supposed to be squared or not?
Well, this introduces our next big tool, dimensions. With dimensions, we strip away the numbers, the magnitudes, and even the specific units, and we just look at the raw, fundamental nature of the quantity. In mechanics, we are mostly dealing with mass, length, and time. We throw these into square brackets, like m, l, and t, to show we are analyzing the actual DNA of the physical property itself.
This brilliantly illustrates how completely different concepts in physics are really just different structural combinations of length, mass, and time. Take volume. Volume is literally just length times length times length, so its dimensional formula is simply L cubed. It's got 0 dimension in mass and time. But force is mass times acceleration. Acceleration is a length divided by time squared, so if you map out the dimensions of force, it perfectly structures out to mlt to the negative 2.
Which leads us to Section 5. This is the big one, the physics cheat code, also known as dimensional analysis. Understanding dimensions unlocks this incredible tool built on the principle of homogeneity. That's really just a fancy way of stating a very simple truth. You can't add apples to oranges. In physics, you literally cannot add velocity to force or subtract electric current from temperature. It makes zero physical sense. Because of this, every valid mathematical equation has to balance perfectly. The dimensions on the left side of the equal sign have to be absolutely identical to the dimensions on the right side.
Let's actually put this to the test. Say you want to verify if an equation like kinetic energy, 1/2 mv squared, equals potential energy, mgh. Break the left side down into its base dimensions. Mass times velocity squared gives you m L squared t to the negative 2. Now do the right side. Mass times gravity, which is an acceleration, times height. It simplifies to the exact same m L squared t to the negative 2. Since both sides reduce down perfectly, we know the equation is dimensionally valid. If you had forgotten to square that velocity during a test, the dimensions wouldn't match up and you'd instantly know you made a mistake.
But it gets even better. You can actually use this cheat code to write entirely new equations from scratch. Let's say you know that the time period of a swinging pendulum depends on just the length of the string and the acceleration of gravity. You can use dimensional analysis to deduce the actual math formula. By balancing the dimensions of time, length, and gravity, you can algebraically prove that time equals a constant multiplied by the square root of length divided by gravity. You literally derived a fundamental law of physics just by matching up the dimensions. No way, right?
So before we close the toolbox on this chapter explainer, it is worth asking, are these foundational rules just set in stone forever? Are our definitions of the meter and the kilogram totally permanent? The short answer, no, they aren't static at all. As our technology gets better, the definitions of base units actually have to be revised to keep up. In fact, the SI system got a major revision quite recently, in 2018. Instead of relying on physical objects, like there used to be a literal metal cylinder in France that defined the kilogram, scientists completely tied all the base units to unchangeable constants of nature, things like the speed of light and the Planck's constant.
So there you have it. You now possess the ultimate physics toolbox for this chapter. You understand the vital importance of standardizing with the SI system, how to honestly report reality using significant figures, and how to verify the very DNA of your math using dimensional analysis. You are completely ready to confidently conquer the rest of your physics journey.
But I want to leave you with this final thought to ponder as you continue unlocking the mysteries of the universe. We've evolved from measuring things with feet and pounds to tying our units to fundamental constants like the speed of light. So as our measuring tools inevitably approach the absolute limits of the quantum scale, how will our foundational language of reality need to evolve next? Thanks for hanging out with me for this explainer, and keep questioning the universe around you.